Okay, then let's continue. This is mechanical properties of solids, a continuation video, where in the previous video, mechanical properties of solids, chapter 8, I have already done stress strain Hooke's law, stress strain curve, elastic modulus, most of elastic modulus. No, I have completed elastic modulus. The only topic left is applications of elastic behavior of materials. Let's go there. There is one prior topic, elastic potential energy in a wire, in a stretched wire. When a wire is put under a tensile stress, work is done against the inner atomic forces. Tensile stress, basically longitudinal stress, when we are pulling it, elongating the wire or a cylinder. When a wire is put under a tensile stress, when we put it under a tensile stress, stress is force per area, force per unit area. When we put it under a tensile stress, work is done against the inner atomic forces. This work is stored in the wire in the form of elastic potential energy. When we do work against the tensile stress, tensile stress we do work against the inner atomic forces. This work done is stored in the wire in the form of elastic potential energy. That is, assuming that the inner atomic forces or the bonds do not completely break, still in the elastic region. When a wire of original length L and area of cross section A is subjected to deforming force deforming force F along the length of the wire, let the length of the wire be elongated by L. Okay, there is, let's assume, a wire of original length capital L and cross sectional area A, and we subject it, we basically pull it using a force F. It is along the direction of the wire. We're pulling it, not compressing it. We are pulling it. Then, due to this stress or due to this force applied, the length of the wire, let's assume it's elongated by small l. Then, from equation 8.8, wherever that is, let's check it out. Yeah, this one. This is Young's modulus formula. Basically, Young's modulus is longitudinal stress by longitudinal strain. Longitudinal stress by, it is the magnitude of the strain produced is the ratio of tensile or compressive stress, or basically in our case tensile stress, to the longitudinal strain. Basically longitudinal stress to longitudinal strain is defined as Young's modulus, and we know stress is force by area, and strain, which is equals to, for longitudinal strain it is delta L by L. So this is the formula we will get, y, which is equals to FL by A delta L. From that equation we have F equals YA into L by L. This is the exact formula, just some shifting is done here, where Y is the Young's modulus of the material of the wire. Now for a further elongation of the infinitesimal small dl, work done dW is F dl or YAL dl by, basically just formula is written here. Basically, if we assume that after this elongation small l, we elongated the wire through the stress with small l, delta L being equal to small l. Now after this elongation, let's assume for some more infinitesimally small elongation of length dl, the work done in elongating the wire for a infinitesimal small elongation is dw. with force F. Okay, now formulas. Wait a second, this is F dot dl or F cross dl, basically work done formula. Work done which is equals to force times perpendicular distance, but since it's an infinitesimal small length, we take it as dl, force times dl, dw which is equals to force times dl, dw which is equals to force times dl. This is what they're saying here, and we know formula of force which is equals to ya by L, and substituting that here we will get YAL dl by capital L. Therefore, the amount of work done W in increasing the length of the wire from L to L plus small l, that is from L0 to L which is equals to L, we use integration. This is the formula here. Work done which is equals to formula here. Just apply the integration. The only thing that needs to be here is small l. Everything else is everything. Wait a second. No, the original length is constant, Young's modulus is constant, area is constant. So only length, the only thing that needs to be here is this L here, that is small l. Small l should be there, everything will come outside, and integration of L with respect to dl is L square by 2, which we have shuffled here and written W which is equals to YAL square by 2L. Now this work done is stored in the form of potential energy. More simplification here, just rearranging the terms. We can write it as 1 by 2 into y into L by L whole square. We wrote it as L by L whole square by making it into L by L. So this L will remain outside, this will become L square. It became L square, and we know that the change in dimension, which is small l, per original dimension, which is equals to strain, longitudinal strain. So here the work done is half times Young's modulus times strain square times A into L, which is equals to volume of the wire. Volume of the wire. This is the amount of potential energy stored in the wire, or the work done to elongate a wire. Or we can also write this as half times stress times strain times volume of the wire. We can substitute Young's modulus value, Young's modulus which is equals to stress by strain. So Young's modulus which is stress, or Young's modulus which is equals to stress by strain. And if we substitute stress by strain, strain square will become strain, and the denominator of stress, that will both will get cancelled. We will get half times stress times strain times volume of the wire. The work is stored in the wire in the form of elastic potential energy only till elastic region. Therefore, the elastic potential energy per unit volume of the wire U is U equals half stress times strain, along with volume of the wire. But here we consider it as per unit volume of the wire. So we divide it by V, we will get half times sigma epsilon. Now let's go to the last topic, that is 8.6, applications of elastic behavior of materials. The elastic behavior of materials plays an important role in everyday life. All engineering designs require precise knowledge of the elastic behavior of materials. Okay? For example, while designing a building, a structural design of the columns, beams, and supports require knowledge of strength of materials used. True? Have you ever thought why the beams used in construction, bridges, as supports, etc., have a cross section of the type I? Why does a heap of sand or a hill have a pyramid shape? Answers to these questions can be obtained from the study of structural engineering, which is based on concepts developed here. Okay. Cranes used for lifting and moving heavy loads from one place to another have a thick metal rope to which the load is attached. The rope is pulled up using pulleys and motors. Suppose we want to make a crane which has a lifting capacity of 10 tons or metric tons. 1 metric ton, which is equals to 1000 kgs. How thick should the steel rope be? We obviously want that the load does not deform the rope permanently. Okay, we saw the points where a wire can stretch till the elastic limit. The wire, even if it stretches, it won't permanently deform, but after the elastic region we will enter the plastic region. At that time, after stretching, it will not be able to come back to its original position. Going even more than that, we will come to the yield point or the ultimate strength, where the proportionality is gone. Let's check the graph itself, where here if we see O to A is the elastic limit, where it will be completely proportional, obeying Hooke's law here. Hooke's law, which says that stress is directly proportional to strain. Stress equals K strain, K is the elastic modulus. O to A is the elastic limit, A to B, where B is the yield point, and B to D, this is the proportional point till this point, where D is the ultimate strength. Till here, the strain will increase and the stress will also increase. Proportionality will be there, but after D, which is the yield point, the proportionality will be gone, and even though with less stress, the strain will keep on increasing. That is the graph here. And we don't want the wire which is used in crane. Let's assume the limit is 10 tons. So if the stress per unit area should be for 10 tons, this area, all the weight the crane needs to lift, the stress should not cross the proportional limit, elastic limit. It should be within the elastic limit. That is, if the crane lifts 10 tons, the crane's wire should not stretch. If the crane's wire should not stretch for 10 tons, the stress strain graph should have a large elastic region. Basically, the OA should be more, the OA region. Okay, let's go back. Therefore, the extension should not exceed the elastic limit. From 8.1, we find that mild steel has a yield strength of 300 into 10 power 6 Newton per meter square. Thus, the area of cross section of the rope should at least be A should be greater than or equal to W by omega Y, that is yield point. Yield strength, not the yield point. It is basically the elastic limit. Yield strength of 300 into 10 power 6 Newton per meter square. Per meter square, the stress should be around 300 into 10 power 6 to permanently deform the wire. It should be more than 300 into 10 power 6 to permanently deform the wire. So basically the formula is sigma y, which is equals to stress, sigma y, which is equals to work done, not work done, it is weight by area. So we already know the yield strength value for 1 meter square when one area is 1. but area will not be 1, should not be 1. So area which should be greater than or equal to weight by sigma y, weight which is equals to uh, 10 tons into 10 or into g, 10 tons into g, which is by sigma y. If we calculate it for that, we will get it that the area should approximately be 3.3 into 10 power minus 4 meter per second, meter square, not meter per second. The area for the length of the, I mean the area of the crane's wire, cross-sectional area of the wire should be more than or equal to 3.3 into 10 power minus 4 meter square to carry a weight of 10 tons, corresponding to a radius of about 1 centimeter for a rope of circular cross section. Generally, a large margin of safety of about a factor of 10 in the load is provided, even though like we are lifting, the crane is lifting only, supposed to lift only 10 tons. Obviously, we can't use a 1 centimeter diameter wire, 1 centimeter radius wire, or 2 centimeter diameter wire. So a large safety precaution is followed with the crane, although only need to lift 10 tons, its wire will be made in such a way that it can weigh 100 tons, 10 times the actual load, factor of 10 in the load, it is provided. Thus a thicker rope of radius about 3 centimeters is recommended. A single wire of this radius would be practically be a rigid rod. So the ropes are always made of a number of thin wires braided together. Normally, if normally like a 3 centimeter rod would be enough, but if this wire is a 3 centimeter, normally it will only be like a rod. It will be a rod, so we don't need it to be a rod, we need it to be a rope. So because of that, a number of small wires are joined together or braided together to form the total crane's rope, like in pigtails, just hairstyle. For ease in manufacture, flexibility and strength, that also it will help. A bridge has to be designed such that it can withstand the load of flowing traffic, the force of winds, and its own weight. Okay, we need to design a bridge. What this bridge needs to do is it needs to withstand the load of the cars, vehicles, everything, the flowing traffic. Second, it needs to withstand its own weight. Obviously, it should not fall down for its own weight. That is the first thing. Second thing, it should withstand all the vehicles, all the traffic. Third thing, it should not fall for wind. Any kind of wind should not fall the bridge. And even minor disasters, it should also withstand minor disasters. Although large scale ones cannot be avoided, at least small scale disasters should be withstood by the bridge, an extra condition. Similarly, in the designs of buildings, the use of beams and columns is very common. The building's whole structure, whole support is through the beams and columns, which maintain the endoskeleton of the building. In both the cases, that is bridges and the buildings, the overcoming of the problem of bending of the beam under a load is of prime importance. Like if we keep a load that exceeds the elastic limit of the rod, then it will obviously bend. So we need to understand how much load the rods can withstand, the beams can withstand, so for the building to remain standing. All this comes under studying the properties of the materials. The beam should not bend too much or break. Let us consider the case of a beam loaded at the center and supported near its end, as shown in figure 8.6. A bar of length L, breadth B, and depth D, when loaded at the center by a load W, sags by an amount given by delta, which is equals to Wi square by 4BD cube y. Okay, let's read that again. Let us consider the case of a beam loaded at the center. Basically, there is a beam and there is a load at the center. Meaning, if there is basically, this is the beam, this is bending right here. This is the beam. If this is the beam, then this is the center of the beam. Center here. Now a weight is connected to the center. A load is connected to the center. That's what they're saying. At this scenario, there is a beam and there is a load connected at the center. And it is supported near the ends. It is fixed at the ends. As shown in figure 8.6. This bar is of length, this beam is of length L, small l. Its length is L. It has a breadth of B and depth of D. Basically, yeah, its depth or height, we can say. But in this case, it's more appropriate to call it as depth. So it will call it as depth. It has a length L, breadth B, and depth D. Now it's loaded at the center by a load W. And it sags, meaning it bends by an amount given by delta, where delta is equals to Wi cube, where I is the inertia, moment of inertia by, no wait, that is not I, that is L, WL cube by 4BD cube Y. Okay. They just gave the formula. The formula is Wi cube by 4BD cube times Y. A beam supported at the ends and loaded at the center. That is the formula given here. This relation can be derived using what you have learned and a little calculus. From equation 8.16, we see that to reduce the bending for a given load, one should use a material with a large Young's modulus. For given material, increasing the depth rather than the breadth, B is more efficient in reducing the bending. Since delta is proportional to d power minus 3 and only to b power minus 1, of course, the length L of the span should be small as possible. But on increasing the depth, unless the load is exactly at the right place, difficult to arrange in a building with moving traffic, a deep bar may bend as shown. This is called as buckling. To avoid this, a common compromise is a cross-sectional shape shown. This section provides a large load-bearing surface and enough depth to prevent bending. This shape reduces the weight of the beam without sacrificing the strength and hence reduces the cost. Okay, let's read that again. We saw the relation here. We saw that the delta that is sagging here or the bending here is directly proportional to the length cube. The higher the length, the higher the bending, inversely proportional to B, that is breadth. So higher the breadth of the rod, the lower the bending, and it is inversely proportional to D cube. It's even more so than breadth. Higher the D cube, higher the depth of the rod, the most low the sagging. It is a 1 by r cube, 1 by d cube relationship, and 1 by b relationship. So if we increase both breadth and depth uh, simultaneously in equal values, the sagging in these two different cases will be the least in terms of depth, because it's a 1 by d cube relationship. Okay, let's see what they have given here. This relation that we saw there can be derived using what we have already learned and calculus. It seems they won't be giving the derivation here. Okay. Okay, from equation 8.16, it seems to be related to Young's modulus. Let's see it. Wait, it is this equation itself, 8.16. From this equation, we can see that to reduce the bending for a given load, one should use a material with a large Young's modulus. And we see that it is inversely proportional to Young's modulus. Higher the Young's modulus, lower the bending. That is one thing here. Large Young's modulus. For a given material, increasing the depth rather than breadth is more efficient in reducing the bending. Okay. Since the bending is directly proportional to d power minus 3 and only to b power minus 1, of course the length L of the span should be small as possible, because it is L cube, directly proportional to L cube relationship. Even for a small increase in length, the bending will be more and more. Increasing the depth unless the load is exactly at the right place. Okay, but on increasing the depth, unless the load is exactly at the right place, the deep bar may bend as shown in the figure. Okay, this is the bending here. It's called buckling. This is the bending when we to avoid this bending, a common compromise is a cross-sectional shape shown in figure 8.7. This will provide a large load-bearing surface and reduces the weight, has a large depth. This shape reduces the weight of the beam without sacrificing the strength and hence reduces the cost. Okay, fine. Let's see that again later if possible. The use of pillars or columns is also very common in buildings and bridges. A pillar with rounded ends as shown in figure 8.9a. There doesn't seem to be 8.9a. There is 8.8a. This is the one. This is a rounded corners. Supports less load than with a distributed shape at the ends. This will support more load than a rounded one. The precise design of a bridge or a building has to take into account the conditions under which it will function. the cost and long period reability of usable material, etc. The answer to the question why the maximum height a mountain on earth is 10 km can also be provided by considering the elastic properties of rocks. A mountain base is not under uniform compression, and this provides some shearing stress to the rocks under which they can flow. The stress due to all the material on the top should be less than the critical shearing stress at which the rocks flow. At the bottom of the mountain of height h, the force per unit area due to the weight of the mountain is hgp, where rho g, where rho is the density of the material of the mountain and g is the acceleration due to gravity. The material at the bottom experiences this force in vertical direction and the sides of the mountain are free. Therefore, there is not a case of pressure or bulk compression. There is a shear component approximately of h rho g itself. Now the elastic limit for typical rock is 30 into 10 power 7 Newton meter square, equating to h rho g, with which we will get it as approximately 10 kilometers, which is more than the height of Mount Everest. What they mean by this is not a case of pressure or bulk compression is, bulk compression is when it is in hydraulic conditions where we put it in water. There is complete compression, there is no change in shape, but there is decrease in volume. It's not the case because even though the top and the bottom have pressures, there is no pressure at the top, but we might be able to consider gravity. There is, and but even though we consider if the top and the bottom are under forces, the sides are free, so it's not getting bulk compression. That's not true. That's what they said here. Okay, let's see the summary. Stress is the restoring force per unit area, and strain is the fractional change in dimension. In general, there are three types of stresses: tensile stress, longitudinal stress associated with stretching, or compressive stress associated with compression, shearing stress, and hydraulic stress. For small deformation, stress is directly proportional to strain. For many materials, this is known as Hooke's law. The constant of proportionality is called as modulus of elasticity. Three elastic moduli, that is Young's modulus, shear modulus, and bulk modulus, are used to describe the elastic behavior of objects as they respond to the deforming forces that act on them. A class of solids called elastomers does not obey Hooke's law because they show a large amount of variation in strain and stress with minimal stress, the strain being many times its original size, like rubber or the aorta tissue. When an object is under tension or compression, the Hooke's law takes the form F by A, which is equals to Y delta L by L, where delta L by L is the tensile or compressive strain of the object, F is the magnitude of the applied force causing the strain, A is the cross-section area over which F is applied to perpendicular to A, and y is the Young's modulus for the object. The stress is F by A. A pair of forces when applied parallel to the upper and lower faces, the solids deformed. That upper face moves sideways with respect to the lower. The horizontal displacement delta L of the upper face is perpendicular to the vertical height L. This type of deformation is called as shear, and the corresponding stress is shearing stress. This type of stress is possibly only in solids. In this kind, even longitudinal as well, it's mostly possible in only solids. Shearing and longitudinal are mostly possible in solids, whereas hydraulic we can see in both gases, waters, and solids. Okay, then in this kind of deformation, the Hooke's law takes form. This is shearing stress, where the force is parallel to the surface, like sliding a book over a surface, pushing a book over a surface. This is stress, which is equals to G is the rigidity modulus or the shear modulus, where delta L is the displacement of one end of the object in the direction of the applied force, and G is the shear modulus. When an object undergoes hydraulic compression due to the stress exerted by surrounding fluid, the Hooke's law takes form, where the Hooke's law is stress is directly proportional to strain in small components of stress. Strain, where P is the pressure, hydraulic pressure, and the object due to the fluid delta V by V. The volume strain is the absolute fractional change in the object's volume due to the pressure, and B is the bulk modulus of the object. And let's see some points to ponder. In the case of a wire suspended from ceiling and stretched under the action of weight F, suspended from its other end, the force exerted by the ceiling is equal and opposite to the weight. However, the tension at any cross section A of the wire is just F and not 2F. Okay, let's read what they are saying here again. Let's assume a wire. It is suspended from a ceiling, and one end is connected to the ceiling. It's fixed there, and the other end, through a weight, we attached a weight. It is having a force of F. The weight is F. That is downwards. It is stretched under this weight. The force exerted by the ceiling is equal and opposite to the weight. The force exerted by the ceiling, which is equal but opposite to the ceiling. That is the reason we can assume that the ceiling is not collapsing, or the wire is not falling down. The force on the ceiling exerted by the ceiling is equal and opposite of that of the wire. This is Newton's third law, where when a wire exerts force on the ceiling will exert a equal and opposite force on the wire, through which they attain a equilibrium. However, the tension at any cross section A of the wire is F and not 2F. That is what we know here. The tension in the, even though both like two forces are acting, the tension in the wire it is not 2F but only F. Because if we consider, even though we assume that the wall is the ceiling is applying a force in opposite direction, or yes, applying a force in opposite direction, it's not actually pulling the wire. The only thing that is pulling the wire, it is the weight applied, the load applied, that is doing it downwards, pulling it downwards. So the tension is only due to the weight, so as such it is F by A. The force, the tension is F, and the stress is equals to tension per unit area is F by A. Hooke's law is valid only in the linear part of the stress strain curve, basically when they are proportional. The Young's modulus and the shear modulus are relevant only for solids, since only solids have lengths and shapes, what I said before. But when if that was the case, then we can oppositely say that bulk modulus is applicable for everything or most states of matter, as solid, liquids, gas all have a volume. Bulk modulus is relevant for solids, liquids, and gases. It refers to the change in volume when every part of the body is under the uniform stress so that the shape of the body remains unchanged. Metals have larger values of Young's modulus than alloys and elastomers. A material with large value of Young's modulus requires a large force to produce small change in its length. Okay, they're saying that metals have larger values of Young's modulus, which is true, and that is more than alloys and elastomers. It's very important to remember they have higher values of Young's modulus than alloys and elastomers. A material with large value of Young's modulus requires a large force to produce small changes in length, which is also true. In daily life, we feel that a material which stretches more is more elastic. That is more conventional. No, it's not conventional, but more talking way of saying things. Like we can say that we say that the material which stretches more is the only thing that is elastic, but that is not the case. It is a misnomer. In fact, material which stretches to a lesser extent for a given load is considered to be more elastic, like steel. Steel, if normal conventionally, if we say, or normally we say, it is obviously seems like it's not elastic at all. But in a more conventional way of saying things, it is the materials which stretch less for larger strains is said to be more elastic. Higher the elastic region, the OA distance, or OA graph, which is higher the region under the OA graph, the more the elasticity. In general, a deforming force in one direction can produce strains in another direction also. If we consider a deforming force in one direction, it can produce strains in other directions also. This is like Poisson's ratio, where we saw that lateral strain is directly proportional to longitudinal, Poisson's ratio, lateral strain is directly proportional to longitudinal strain. This is because as the area increase, when let's assume for a rod of uniform length, let's assume there's a rod which has uniform length and uniform volume. Let's assume only volume. The rod has uniform volume. Assume we are stretching it, we are elongating it. When that happens, the length increases, but if we consider the radius of the wire will keep on decreasing. That is to conserve matter, that is to maintain the volume should be maintained. As such, the as the length increasing as the length increases, the area decreases, the radius decreases. So there is not only change in the longitudinal direction, where is the increase in length, but also in the area that is perpendicular to the direction of the force. Normally there is no work done in that direction. When force work done, which is equals to FD cos theta, cos 90 is 0, so work done should be 0. But there is, even though the work done is 0, there is still a force, there is still a change in, there is still a strain produced there. That is the Poisson's ratio. Poisson was the first to observe it or to point it out. So that is the case. Now let's read this again. In general, a deforming force in one direction can produce strains in another direction also. The proportionality between stress and strain in such situations cannot be described by just one elastic constant. For example, for a wire under a longitudinal stress, the lateral dimensions, radius or cross section will undergo a small change, which is described by another elastic constant of material called as Poisson's ratio. Stress is not a vector quantity, since unlike a force, the stress cannot be assigned a specific direction. force acting on a portion of a body on a specific side of a section has a definite direction. Okay, then with that, first revision of this chapter is completed. First revision completed. Okay, then, although this is a part video, it did take 45 minutes.